the term commutative means whether these two, for instance, if we have a sequence of rotations such as Rx, Ry, Rz, in these cases, if we have certain degrees such as 45 degree, Ry 90 degree, in this case, for instance, for given the such as a plane here, if you apply this rotation, and we have shown you the slider, right? If we switch their order, right? For instance, perform Ry first, because in our interpretation or explanation, we usually use this direction. For example, given an object here, apply transformation, apply transformation. If we reverse their order, and the result will be different. Of course, in some cases, the result could be identical, but in most of the cases, it will not be identical. So not only the rotation, for instance, if we have translation here, if you arbitrarily move the translation somewhere, their result will be substantially different in most of the cases. Yeah. Of course, in some cases, you may luckily get an identical result, but it's quite rare. Okay. So the transformation itself is not commutative. Okay, so you have to, so in your homework number 1, you have to carefully design your transformation order. Yeah, otherwise your plane or your helicopter will, yeah, somewhere else do not meet your expectation. Yeah. Okay, so that is one issue we have talked about in the last lecture. And in the end of the last lecture, we talk about idea, the so-called rotation about such as some fixed point. We mentioned that in our, for instance, graphics design, if we want to control some object, such as you would like this cones rotate, given a certain point, such as the center of the point. And in these cases, if you apply the so-called global transformation or a common transformation, common rotation metric, such as R here, the 45 degree, then it will move to such as like this way. Yeah. And because all of our rotation is derived based on the, say, certain such as z axis, and after rotation, you will keep its radius identical, right? So if you want to rotate by regarding to this point, we have to use some combination of transformation. Yeah, this idea is sort of like, for instance, we have sun here, and we have such as Earth here, right? And for instance, I think most of you have known that our Earth will rotate along or around our rotation axis, right? So in Chinese, we call 自转, right? And at the same time, it will also perform another rotation. In English, we usually call revolve, right? Revolve. It usually means 公转, right? I mean, we rotate around such as the sun or some other, such as the center of the galaxy or something like that. Yeah, but currently we restrict our discussion into the solar system. Yeah, so we rotate around the sun, right? So if we, in this case, if we take this location as origin, we apply rotation metrics such as RZ here, it will rotate like this one, right? And it will be revolve around the sun, right? And if you want to estimate or perform the so-called rotate around its own axis, such as the tilted axis, usually known as 23.5 degree, right? As I remember. So, or some other, it may change sometimes. So we have to do a combination of rotation, transformation to reach these results. So in these cases, if you rotate such a, let's simplify this problem. We try to rotate at such its own z-axis. So its idea could be, say, we can, for instance, if we have already have Earth here, then we can move, such as we have Earth here, and the Earth already here, and we can use the translation, move back to the sun, right? That is the origin. And then we can do the rotate. If we simplify this problem as so-called rotation around the RZ, right? Rotation theta here, and then we can then move back. That is TS here. So we can move to here, right? So in this case, we can do the so-called rotate, right? And if we want to concurrently do the so-called rotation around our self-axis, and we also want to revolve, right? So we can, after do the rotate, we can also apply, such as after here, then we can apply revolve, such as y phi here. Right. So we can combine multiple rotation and transfer. So in your code sometimes, or in your design, sometimes you have a sequence, a very long sequence of rotation translation, but we will divide and conquer or make them into sort of like a hierarchical structure to simplify the implementation. Yeah. Yes. I want to emphasize is that we can use this kind of such as combination of translation, and we can turn our unknown rotation to some rotation we already know, such as rotate around the at the origin, and then do what we have learned and then move back. So so we can do the rotation around the self-axis and revolution. Yeah. Okay, so that is what we have learned in our last lecture, right? Okay, so based on this idea, we actually can also extend what we have learned to some other more complex transformation. Yeah. And so one of the we can say popularly used is so-called rotation about arbitrary axis. Yeah. So what is arbitrary axis? For instance, when you have such as some airplane here, so for instance, we have some plant. Okay, so we have a plane here, and because for instance, this is the world coordinate x, y, and z, right? But when we do our airplanes, we want to control airplane. What we usually do is, for instance, we have a local coordinate, right? For instance, this could be the local, such as z here, and this could be such as local x here, and we can have a local y here, right? So that is the so-called local coordinate of the airplane, right? So if you want to, for instance, you play a game, such as some video game, you would like to such a pull up the head of or a tip of the airplane, right? So in this case, what you do is actually the so-called rotation around, such as the local x, right? Because you want to pull up, and sometimes you do some such a rolling this way. It is actually rotate around such as z here. this is the local z. This is the z of the airplane. And sometimes you want to such as u to the right or left. In these cases are y, right? So in these cases, our rotation is actually performed on such non such as the x or y or z. That is the axis of the world system, right? So we have to, in this case, we have to deduce this kind of rotation for some arbitrary, because this z compared to the global is the kind of arbitrary axis, right? But we can reduce this problem or simplify this problem. We can skip this kind of transformation, such as the transformation between the parts. For instance, if we rotate along this way, we can, for instance, move using translation to move to the origin and do the following process. But so we reduce this problem or focus on the problem about, for instance, if we have an arbitrary axis just like this one, but we move this z to here, or we use another name, such as we can call this vector as u here. We try to do the rotation around the u-axis. Yeah. So how can we do that? So let me define the problem here. The first thing is we have arbitrary vector u here, but we usually use the unit vector to process the axis, so we can normalize then as a v here. So their v is component is alpha x, alpha y, and alpha z, right? So this is an arbitrary axis. However, we have learned based on the idea we have talked about, such as rotate around a fixed arbitrary fixed point. And what we have learned in that section is that if we have something new and complex, perhaps we can map them or transform them to a certain base that we already have learned. So the idea is that if we have no idea how to deal with the rotation around this point, this axis, arbitrary axis, perhaps we can try some way to, such as turn this problem into some, such as in this example, we will try to turn them into a RZ rotation. So we have to do some combinational transformation to move this axis gradually to here, and then we can gradually move back. So based on this idea, because we already learned the RZ here, so we can use some cascading or combination of transformation, and we don't have to derive, or you can say deduce a new two equation or a new matrix. Okay. So the hint is that because we have already learned some transformation, so we can map this complex problem gradually to a simpler one. Yeah. And then we can move back. And then we will keep the operation correct. Yeah. Okay, so with this vector, then we will make use three angles here. We call them phi x, phi alpha, phi z. So that is the angled. For instance, we have here, and we have say projection onto such as onto these axes. So there will be such as vector projected here, and we have the included angle here. Okay. And so, for instance, because we have known that we have such as alpha x, alpha y, and alpha z, right? So we have a vector here, right? So the cos because this is unit vector, right? So with projection of length could be, because the vector here, it could be say alpha x, right? So alpha x will be the cosine phi x. Alpha y will be cosine phi y. Alpha z will be cosine phi z. And because it's univector, so the sum of square of this alpha will be 1, right? Okay, so let me use conceptual flowchart to let you know the concept. So first of all, if we have arbitrary vector like this one, sorry, this could be v, right? Because u is being normalized. But for instance, here we can assume u equal to v, and then all have vector unit vector. Okay. Okay. So our idea is if we have a point here, we want to rotate these points, such as do some rotation, such as like rotate this rotation based on such as some certain theta here, right? But we have no idea how it can be, what matrix is, so we can move our vector u to u-prime here. Yeah, so the definition of u-prime is we can do a rotation, such as we can rotate do some certain rx here. With this rx, we can turn this axis onto, say, the xz plane. Okay, so you can think about if we have a point here, we apply the transformation rx, you will rotate to here because you rotate along the rx, right? Then afterward, then because our u-prime is already on the xz plane, then we can do such as ry, right? Can turn this axis here. So this point, if we apply this kind of transformation, you will move to here, right? So you can think about we have a p here. If we apply such as rotation x first here, it will move to here. The axis is on the xz plane, but the p plane would may not be on the xz plane. And then we use the ry to move the axis to here, and our point will move to here, right? And at this point, we already know we have learned such as through these two transformations, we can turn our u to such as u double plane here, right? Then with this process, the following will be simple. The process will be simple because we can then apply such as rz here, do the theta here, right? And then we can reverse process, just like the rotation around the fixed point. Then we can inverse this process, then move back here. Yeah. So let's show you how to estimate these two metrics. Because if you have these two metrics, that is the combinations r-axis, you apply such as rz here to do the theta we want to perform, and then we can do the inverse process to move the whole thing back. Yeah. So the point, for instance, should be here, right? Theta. Yeah. Okay, so the first step is we have to rotate the u to the u plane, onto the rz plane, right? Okay, so because this vector we can project them, because what we would like to do is do some rx, that is rotation around the x-axis. So you will have to find the theta here, right? And if we have a vector here, and we can if this point is alpha x, alpha and y, its projection is simply say remove the x part. So this point could be alpha, say y 0 and alpha z here, right? So because we have this vector, we can simply estimate the so-called the theta here, right? Theta x here, right? And one idea is that, for instance, if we already have such as this one is because the original u here is a univector, right? So the length is 1 here, but d, because it's a projection, so it's actually is d should be, this length should be smaller than 1, right? But the d is equal to such as alpha y squared plus alpha z squared, right? Okay, so we have this one, and we also have such as rz. And ry, we actually can estimate such as cosine theta and sine theta. So one way is, for instance, we can explicit estimate such as ry divided by d. It will become so-called sine, right? Theta. So we can also estimate using the sine inverse to do y, right, to get the theta. But what we want to get is only sine and the cosine theta, right? So these two information can explicitly get from d alpha y and alpha z. So in this case, we don't really have to estimate the explicit to extract the theta. We can simply use the vector content such as alpha y, alpha z, and d to get the corresponding sine and the cosine theta. Yeah. So here, show the result. For instance, we can have a cosine here, and we have negative sine here, and we have sine, we have sine here, right? So given this vector, we can simply estimate a d here based on the alpha y and alpha z. Then if we already have a d, we can simply divide divide alpha divided by d. We can get this the corresponding sine and cosine. Yeah. So we can get this rotation Rx, the first step. And then afterward, we want to estimate the rotation from u-plane to z-axis, right? And so we have to figure out the theta y that can help us rotate from u-plane to here could be, say, you can say u double plane, yeah. Or but in this case, then use oh sorry, the u double plane is this part, and d plane is projection, yeah. Okay, so because for instance we when we apply such as Rx to some vector here, after rotation we have mentioned that it's after the rotation around such as x-axis is valued, x value will be identical. So in this case, its result could be alpha x point 0, 0, because it's also z is not 0, y is 0, okay, and z is not 0, yeah. Anyway, but we can make sure that these vector could be alpha x, right? Because we already have alpha x, and we have said the u-plane is a univector because we simply apply the rotation matrix, so we can get the d-plane, right? So because d-plane square d-plane plus alpha x square could be u-plane, yeah. So once again, we don't really have to explicitly estimate the cosine side because this is a univector. This length is equal to 1, right? So if we want to get the cosine, you can simply get d plane divided by 1, and its sine is simply alpha x divided by 1, right? So based on, as long as we get the d plane, we can get the the cosine, and the sine will be relatively simple because we directly get the alpha x, right? Okay, this whole process will be like, let me show you a PowerPoint step by step. Yeah. For instance, if we have a point here, right? So we can apply the Ix first, right? So the P prime point will be here. And then we can apply the Ry to turn our U to U double prime. U double prime will be, say it's meet, or you can say along with the z-axis, right? So our P double prime point is follow the transformation and reach here, and then we can apply the RZ here. When we apply RZ, the point here will be called P triple prime, right? Then we can perform the inverse process, but we have mentioned you actually have to get R axis and get the transpose of R axis, because transpose is equal to the inverse, right? As we mentioned in last lecture, but here I decompose or let you know the step by step. So we have P double prime, triple prime here. When we apply the inverse process, it will move our system to here, or sorry, move our the P double prime to P, it is full prime, yeah, quad prime, yeah, and it will be here, and then once again we apply the inverse of Rx here, then it will move to here, right? So yeah, what we our goal is try to find a theta here. But we can decompose this process as a sequence of combination of transformation and then inverse of them. Then we can accomplish this arbitrary axis rotation. Yeah, but I want to emphasize this is just a way to let you know we can, because you have learned the basic transformation, you can use a combination to accomplish some difficult one, right, or complex one. But we actually have some, such as some formula for rotation about arbitrary axis. They will have some relative complex. For instance, when you check the rotation matrix of rotation arbitrary axis, you will kind of commonly will have some square divided by something. It's actually derived from this sequence of transformation. Yeah. And luckily, if you perform such as OpenGL, rotate, GL rotate, you actually then provide this kind of function by OpenGL. Yeah. So for instance, you can provide your angle. Your angle would be, say, a radian. Yeah. And then you can provide the axis such as alpha x, alpha y, and alpha z. Right. So OpenGL actually provides this kind of rotation about arbitrary axis, but for most of cases you want to you may use it such as use 1 0 0. That means for rotation axis, and this will make you such as easier to decompose or analysis a problem. And if you set your angle as 0 1 0, that means your rotation around z, right? 0 0 1, it will make your rotation. Oh, sorry, should be z. This should be y. Sorry, this one should be y, and this one should be z. Right. Okay, so that is the rotation about arbitrary axis. So you don't have to worry about you have to do this every time. It's just let you know how this kind of matrix is derived, right? So for OpenGL, we can simply call the API to deal with this problem. Yeah. Okay, so we already know such as given a transformation, or given a sequencer transformation, we can do something more complex compared with simple rotate, simple movement, right, or translation. Yeah. So one of idea is called instancy, right? The idea of instancy is that, for instance, if we have some model here, such as, for instance, you have a tiny Pikachu here. But based on some combination, you can move. For instance, our model usually, for instance, when you load your model, the model usually stay in such as in the origin, uh, of the world. Yeah, but you can based on sequential transition, you can move to here, and of course, we have mentioned you can scale up the Pikachu here, right? Okay, so uh, for instance, you can uh, such as translation, scale, right, and rotate. So you can uh, you can generate a bigger Pikachu at certain location, right? And given the same model, we can also move the Pikachu to here. For instance, but it's face toward this one, right? So this idea is sort of like our object-oriented OOP idea. For in this, your basic model could be such as a class, right? And then you have some instance that is the object you code. So that is derived from the class, right? So this is the instancy. That means you generate some new uh, object based on this class, right? The idea is similar. Yeah. Okay, so we can start with a simple object, then we can use rotation, translation, and others, and adjust its size and move. And we can base on this idea to control this model, right? And we usually like to use such as because we do the scaling, because we have mentioned if you translate here, do the scale is actually moved to here, right? So it will not only increase its volume or height, but it will also make the object, if you as such as twice the object, it will actually move its distance. Uh, for instance, twice from the origin, right? So we usually like to such as scale something at the origin. So we sometimes put the scale first at the origin and also rotate at the first one time and then move to the location you want to reach. Yeah. So this is a function if you object here or P here. Sometimes we usually use conventional. We like to use such as SRT, right? Have a P plan here, so we can move our such as this phase to here, right? So it will be easier for us to control, yeah, to intuitively control. Okay, so however, sometimes in addition to such as a single rigid body object, for instance, we have mentioned the instance here is actually, for instance, the instance of this smelting phase is actually a rigid body, not a rigid body. We can use say this kind of transformation called similar transformation. That means the rotation transformation include the scale, because you scale something up is no longer rigid body, but it still keep its relative rate structure, right? Yeah. So if we use rotation translation, it can accomplish rigid body, including the scale. It will become a so-called similar transformation with in a similar shape. Yeah. However, sometimes we cannot simply use such as SRT to accomplish some more complex object. So in a lot of cases, such as in the left-hand side, this is one of the for instance, when you take a look at the Pixar's movie, right? Sometimes you have a P, X, A, R, and lamp will jump, boom, 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 boom here, right? Become its eye, right? So this is one of the Pixar's early famous short films called Luxo. Yeah. So there is cute and you can say naughty lamp here. Yeah. So, but in this, you can observe that this lamp will definitely not a rigid body, right? Because it have a base here, so you have some joint here, joint. So those joints are uh, a rotation here. So we have rotation here, rotation. So it's the object itself could enable multiple rotation. Yeah, and there's also a bone between these joints for rotation. Yeah, and it's not only for this kind of such as furniture or the lamp. Sometimes what we human actually can use this kind of representation. For instance, this is the Star Wars C3PO, right? So it's actually based on such as a skeleton structure. Yeah, so we have some leg here, we have the torso here, and then we have some skin. So you can observe we have a lot of joint here, joint. Yeah, to control. Even this kind of this robot look like a trash can, but it's also a famous one called R2D2, right? So it's actually and also you can say a hierarchy structure because we have some joint here, we have a skeleton here, so we have another joint. So we also, so this is a rigid body, but we have a joint here, right? So in a lot of cases, we actually can use, we have to use this kind of joint and bone to represent object, right? So we usually call this kind of hierarchical structure. That means that if you take a look at such as the 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 luxo, that is the lamp, you will have a base. You will then have another joint, and then lampshade here. So it's a hierarchy. It's sort of like a root here. And this could be just like a tree structure. So this could be the child. This is the grandchild, right? So this is a hierarchy system. And for human here is also similar. For instance, if we want to model some human, not only for robots, for humans, we usually use such as here as our root. Then we have some branch for torso, right? And the leg, and leg have their child node. So this kind of structure will sort of like we say a tree structure or a hierarchical structure. Yeah, hierarchical in Chinese means 阶层. Yeah. Okay, so our next step is we try to construct this kind of hierarchical structure. Yeah. So in the following discussions, we assume that because all our objects have to have some points at the origin, right? So we assume that this white, you can say dot or circle, is originally at or align with the root. Yeah. So for instance, we object this part is at the origin. For instance, we have a origin here. This lens shape is point was when you load this model, this point is original align here. And for instance, this light blue one here also is this white one, white joint is aligned with the root. We assume that these joints are originally at the root, right? So we have to two questions. The first one is we have to make, because we have multiple components, right? We have 1, 2, 3, 4. 4 components. We want to make the these 4 components as a hierarchical structure. And for instance, first step, we will try to make these looks or this lamp stand up. Yeah, we want to do this one, right? So first step is we have some additional information. The first one is this part, this lane is D1, and this part is D2, right? So given these two information is not that difficult. For instance, because this base is at the origin, so we don't have to do anything. But for this part, is original stay here. So the dark blue one is we don't have to do any transformation. But the next part is we have to move this one, the light blue one, to the correct location. So the idea is quite simple because it's originally at the origin, but we can simply apply the transformation such as TD1, right? So you can move up. We assume D1 is a vector here. So we can apply TD1 to move lane here. And the lane shape here, we can apply such as TD1 plus D2, or is equal to such as D1, TD2, right? Okay, so this is for the transformation. For instance, we have to move the point to its starting point, like this one, to stand up this or set up this this luxo or the lamp. Yeah, and you just use the PowerPoint to show you when we apply such as two translation, we can move them up. But this is just a static object. Our next question is, how can we do like this one, right? So how can we move such as our luxo to just like the right hand side is slightly bow to the right, right? So we have to include some additional information. That is, we usually use, because it starts to rotate around some angle, so we can define some such as two angle here. The first one is we hope that the dark blue one can slightly rotate to in counterclockwise directions by theta e, right? And then if you apply this one here, yeah, and if you apply to the whole system, your lamp shape will like this one, yeah. And the next step is another angle is we can hope that our light blue one can move to the right with theta b, right here. And next, we hope that our purple lamp shade will move slightly forward by a theta c, rotate by a theta c here. Okay, so we have to find the transformation for individual component. Yeah, so the first step is for the dark blue one. It will be really simple because what you want to do is only r theta a, right? But for this part, it will really be slightly complex if you base on such as the idea of the SRT. For instance, we may have to such as find out the transformation here. For instance, one idea is we can apply our theta b right? But you have to move, instead of move, for instance, if you simply move TD1 here, it will stand here, right? So, but we have to calculate this vector. We have a new spatial distance, such as D1 plan here, right? But D1 plan itself is actually some combination, such as it could be TD multiplied by some R or some other number, right? And then a complex one is for the purple shade, because if you base on such an SRT idea, but here we don't have to scale, so we have to rotate and translate, right? So you have to figure out certain, such as, for instance, the angle here is, even though it's theta c, but compare with such as this part, the theta c is only cover this angle, right? So the rotation compared with this one is actually influenced by its parents, right? So you will include not only the theta c, but also theta a and the theta b. And for the translation, we have to calculate this vector. For instance, this blue vector here. And the blue vector is relatively complex because you have to find this one, because we have known that this could be, say, t rotated by such as theta a, right? But based on, you also have to estimate such as the vector here. So it will relatively complex, such as this another, so this is d1, d2 plus d2, or some other rotation. Yeah, it is countable, but you can carefully calculate, you can get a result. But in this case, it's not easy to simply get such as RT directly, right? So in our in our next, because I think some of students, after several minutes deduction of the rotation sequence of rotation, feel kind of dizzy. So I will stop our my recording here, and in our next lecture, we will further talk about how we can systematically, or using a more easy way, to write the rotation translation for hierarchical system.